Okay. I'm sure all the people that are not here today have a good reason for not being here. Okay. So it is Good Friday. One more section. It's our last section. So imagine you're happy about that. I'm happy about that. Everybody should be happy. So this is a section where another one of these. Okay, we're kind of getting into that territory now that we've talked about so much stuff in here. Another one of these sections where it'll take like 5 minutes for me to show you the rule, and then the rest of it's all about applying it. So short. The only reason why we have even 17 slides is because I left 2 examples from the textbook in there. Okay, so not a long section, but you do need to do enough practice on these that you get the hang of doing this rule. Okay. So, in the rule, we're doing integration still, but we're using substitution. We're substituting in a different variable. That's what we're doing. So, if we have something that we want to integrate, some function, or that we want to find an antiderivative for, you can think about it that way, that is not one of our more basic functions that we just have the rules listed out for, okay, then sometimes, okay, something that we can do is we can substitute in another variable. And if we substitute in another variable, sometimes it works out nicely where then once we've rewritten this using a different variable, the thing that we end up with in the new variable is something that we can integrate using our more basic rules. Okay. So really nice when it works. Okay. So let's look at this one. So we want the integral, or want the antiderivative for 2x times the square root of 1 plus x squared. That's not one of our basic rules, even if you look at the weird, more obscure trig ones. And we do have some square roots involved in there, so that might be something you would think about, but this one doesn't follow directly even from those. Okay. So what we're going to do is we're going to introduce a new variable, and typically what you see used is u. Okay, so sometimes you'll hear this called u substitution. You could use any variable you want, okay, but that's kind of the standard for teaching this, is to use u. Okay, so what we're going to do, and this is the part that really takes the practice, is seeing what of this, because we got this whole function, what part of this should we call u? Okay. And if you kind of got the hang of chain rule, that helps, because really what substitution is it's like the backward version of doing the chain rule. Okay. Also, something that can help is you can think about starting from the inside out. Okay, so think about like the order of operations. If we wanted to evaluate this thing, what's the first thing we would have to do? So here we've got 2 things. We would either multiply our number by 2, or we would square our number and then work our way out from that. Okay. It's not always the very first thing, but typically what we could say is that what we want to substitute for u is like an inside function. So it's part of the inner stuff. Okay. And then that will simplify things for us a little bit. Okay, so what they're doing on this one, okay, is they're using 1 plus x squared. So this part they're calling u. Okay. When we do that, okay, when we pick something to use for u, and it's okay if you pick something and it doesn't work, okay, you just have to try again. But what they're doing is they're picking the 1 plus x squared to be u, and then we think about what we would have left over out here. Here we would have a 2x, and then we've got square root. That's okay, that's square root of u. But we would have 2x, and then we would have dx. So what we would do is we would take and take the derivative of both sides here. And it looks a little bit weird because they're thinking about it in terms of something that we haven't talked about, the differential. All they're doing is they're splitting the, so if you, let me back up. If you took the derivative of u, and with respect to x, we would get du dx. So what they're doing is they're just splitting the du dx part up. Okay. So like we would have du by itself, and then we're just going to put the dx part on the other side. Okay. It's just it's really a mechanical thing that you don't really have to think about, but that's what's happening. So then if we took the derivative of 1 plus x squared, what would that give us? So the derivative of 1 would just be 0, and then the derivative of x squared would be 2x. Okay, and then we're going to write down the dx that we moved from the other side. So we would have du dx equals something. So we just multiply both sides by dx. Because what we're wanting is we're wanting to end up with du equals something. Okay. And so as it turns out on this one, okay, the u part takes care of the part underneath the square root. And then du would be 2x dx, which is everything we have left over that has an x in it. Okay. So this 2x and dx are going to get absorbed into the du term, and then we'll have square root of u. So that's what's going on here. We said this part was u, so they're writing square root of u, and then the 2x dx part, that's du. So now everything's written in terms of u. That's our goal, okay, is to get it where we don't have any x's anymore. Everything's in terms of u. Okay. And from there, that kind of leaves some of the details out, like textbooks seems like they always do. I don't know if they're trying to save paper or what. I don't know why they don't just try to make things clear. That would be this. Right? We rewrite square root of u as u to the 1/2. And then we would find the antiderivative there. That's just the backward power rule. Right? We add 1 to the exponent, get 3 over 2. Flip and multiply, we get 2/3. And then plus c. Okay. So here to here is just our regular antiderivative stuff we've been doing. Okay. And then the only other thing we've got to do is, this is antiderivative in terms of u, but that's not what we were wanting when we started. We wanted an antiderivative in terms of x. Okay. So all we do is we undo our substitution. So where we had u, we just plug back in the 1 plus x squared. Let me get this thing. Okay. So the u is just a tool. We're still starting here and then ending up here like we normally would. We just kind of go through the path of doing this substitution with u, and then we undo it at the end. Was to, all right, because if we do just the u substitution, we've got that part, right? But then we still have a 2x and a dx. So what we would have square root of u times 2x dx. And we got to have something to do with that to get that in terms of u. Okay. And also, another thing to think about is that if we got square root of u, we also need a du. Okay. So it's nice for them to match up. So when we take the derivative of both sides, and on this one, okay, it's set up so substitution works, and we get this situation where the 2x dx part we can rewrite as du to get it all in terms of u. Okay. There's a little bit of hand waving going on, but it's not much, and it's not really important. You can do these mechanically and not have every bit of the theory, and you're okay. Okay, so let's get the actual rule. Okay. This part's just showing you can check it if you work it backward. We took the derivative of our antiderivative, we should get what we started with. So there, we get 1 in the front, and then subtract 1 from the exponent, we get 1/2. No, we don't get 1 in the front, we get, we get 1 in the front, subtract 1 from the exponent, and then we would have to do the chain rule, so we'd have to multiply by the derivative of the inside part, which is 2x. But then we end up with what we started with, so it works. So here's one way you can write down the chain rule. Kind of using this idea as we've got an inside function and an outside function. So if you think about it like that, then you can write the chain rule down in this form. It's a little messy because I got so many parentheses, and it really makes it look harder than it is to use it to me. So it says if we have a composite function times the derivative of the inner function, okay, then we can get the antiderivative of the composite function plus c is our antiderivative. That's kind of write it in chain rule form. To me, the version that makes more sense to write it down is starting, so this goes both directions, okay, is starting this way. Right? If we've got a bunch of garbage, okay, then if we can substitute part of that garbage for some variable so it cleans it up, so there we substitute g of x for u, and so g prime dx turns into du. Okay. Then we just find the antiderivative of that, and then undo our substitution. Okay. So that's kind of what this one's saying. And yes, it's a little bit funny that we use u, and so you get a bunch of FU's in there. So, okay. No, I don't know. I guess they thought we would be mature about it. Okay. So there's saying we can clean it up. Okay, make a substitution for u, and then find that antiderivative, and we're good to go. Okay. All right. So let's do some more examples. Okay. Really, the challenging part on these is figuring out what to use for u. And then sometimes making du come out right can be a little tricky, but we're not going to get too crazy with that. So let's see, let's do this one. So we can't just jump straight to an antiderivative on this one because we have one function inside of another function. We've got a composite function because we have a 2x inside the cosine instead of just an x. So we could try u substitution. And on this one, if we try the inner function as our u. Okay. So typically what working these boils down to is you pick something you think will work for you, and then you take the derivative and see if you can make it match up with everything else you got left over. Okay. So on the u side, when we take the derivative, we'll just have a du. And then if we take the derivative of the 2x side, what's our derivative going to be over there? 2, and then just always remember to write a dx. Okay. So we took the derivative. You can think about it like that, like it represents taking the derivative. Okay. So this one we got just a little bit of adjustment to make on the du because so far, so we got this, u is 2x, so that's this part. The part that we have left over cosine of u we can handle. The part that we have left over is just the dx. But over here we end up with 2dx. We just need dx. So if we have 2dx and we just need dx, what can we do? Yeah, we can divide both sides by 2. Or what's probably going to be a little more convenient for us, a little bit more convenient way to think about it is we can multiply both sides by 1/2. So we end up saying half of du is just dx. So then now this is going to take care of this part. Okay. And the 1/2, where it comes into play, is we can put it out front as a constant factor of 1/2. Okay. So then we'll have cosine of u du. So this part goes there, comes from the part I got in the red box, right? And then this part comes from the green box. So sometimes we do have a constant factor adjustment we need to make. That's not too bad. You just divide both sides by whatever the constant factor is, and then you can just put it out in front of the integral symbol because it's a constant. Not too much of a headache. So then, now with cosine of u, we can find that antiderivative. It's just one of our basics. We'll have 1/2 times, what's our antiderivative of cosine? Sine, yeah. You do have to stop and think about, I do have to think about, okay, if I take the derivative, I get a negative. So yeah, we get sine of u plus c. Or we could just write that 1/2 of sine of u plus c. We don't have to worry about multiplying the 1/2 times the c because half of c is just c because it's just an arbitrary number. And then one more step, we wanted the antiderivative in terms of x, so we just undo our substitution. So instead of sine of u, we got sine of 2x. And there's our antiderivative in terms of x. Questions on that one? Okay. Let's do another one. Let's do this one. So that one's a little messy. Got x times e to the negative x squared power. So this is a really nice illustration of how doing substitution can help us. Okay. So we want to kind of start with an inner portion as our try for u substitution, and as you do more of these, you can kind of look ahead and pick out what you should use for u. But again, if you pick something for u and you can't get du to work out right, just try to pick something else. Okay. Sometimes there's even more than one way you can do them. Okay. So, anybody got a shot you want to take for u? Negative x squared, I think, would be a good choice. And then if we try taking the derivative of both sides, we'll have a du over there. We take the derivative of negative x squared. What do we get? We'll get negative 2x, and then we'll put our dx over here. Okay. So right now, this part's handled by u. The thing we've got, the stuff we've got left over, we've got e to the u. Okay, that's handled. That's in terms of u. But then we've got an x and a dx. Right now, what we have is we've got a negative 2x and a dx. So we just need to make a little adjustment. We don't need negative 2x dx, we just need x dx. So what can we do? Yeah, divide by both sides by negative 2. Okay, just cancel that part out. Or slightly more convenient way of writing that is we can multiply both sides by negative 1/2. Get x dx. So then that's what we got left over. So we can rewrite this integral. Take the negative 1/2 and put it out front. And then we can write it as e to the u du. So the 1/2 du, or negative 1/2 du takes care of the x dx part. And then this u takes care of the negative x squared part. So we're in good shape. And then e is one of our easier ones. What's our antiderivative? Yeah, so just e to the u. Let's see. And then we want to rewrite it in terms of x again. So that'll be negative 1/2 e to the negative x squared. Let's see. And to me, it is not at all obvious to try to make the jump from saying, oh, that clearly the antiderivative of that is this. That's not easy to see. So the u substitution is a good tool in that case. Yeah, 5.5, yeah. Last section. Questions on that one? Okay. You don't always have a constant factor you have to deal with, but sometimes you do. Okay. Like that first one we didn't have that. Yes. It didn't work. Okay, so let's do this one again, and we'll pretend like we're not as smart. Okay, so let's see. Maybe we would try u equals x. Then if we find du, that would be 1 dx. But what I'm trying to make it match up is x dx. And I don't have any way of getting an x out of that because I've just got a constant. So I don't know, that one's not going to work. Maybe we could try e to the negative x squared. And then if we try to find du, that gets messy. So we'll have e to the negative x squared times negative 2x dx. I'm using chain rule there. And then I don't need another one of these. So mark that one out. Because I don't have a good way of getting rid of that, so mark that one out. Yeah. So if you can't figure out a way to make du work, then you know should probably be something else. Yeah, well, on this one it was x dx. On the first one, the thing we were trying to get was it x dx on it too? Well, scroll screen. Yeah. On that one, we just wanted the dx. You just look at what's left over, whatever x terms are left over. Let's do another one, give us something else to look at. And you get a better feel for them the more examples you look at. Made that a little long. Okay. So this one's kind of similar to the first one we did. So this one, I think we should try the part underneath the square root as our u. And then du, the derivative of x cubed would be 3x squared. Derivative of 1 is 0, and then we're finished, so I'm going to put down our dx. Then that's almost matched up. The part we're trying to match du up to is x squared dx. We've got 3x squared dx. So what can we do to adjust? Yeah, divide both sides by 3 or multiply both sides by 1/3. So now this matches what we've got left. So for that part, we can put the 1/3 out front as a constant. We'll have square root of u, and then du takes care of the rest of it. So the 1/3 in the du take up the x squared and the dx, and then u takes up the x cubed plus 1 part. Okay. So then what? Square root of u. What can we do then? Yeah, if you're thinking ahead, yeah, that'd be u to the 1/2. So our antiderivative would be u to the 3/2, 2/3 up front, and then plus c. So if we simplify that, that's 2/9, u to the 3/2 plus c. And then we don't want to leave it like u, we want to rewrite it in terms of x. So u was x cubed plus 1. That's what we used. The final answer, we got 2/9 times x cubed plus 1 to the 3/2 plus c. We're just done doing our substitution there. Again, to me, that is not obviously the antiderivative of what we started with. You could check it though. We could check it. We did the chain rule. That's not hard to check. But a little hard to come up with without using substitution. Maybe a lot hard. Something that might be tempting, a u that would be at least a lot harder. I'm thinking it probably won't work. But I think let me do it in red. I think a bad choice for you would be just the x cubed part. Because then you would end up with u plus 1, and then we're still stuck. We don't have a way to get that antiderivative, even if you could make du work. So yeah, we could make du work on that one, right? That would du would be the same thing. You could do this, but then we would end up with square root of u plus 1, and then we still don't have a good way to get the antiderivative there. Okay, questions on those so far? Okay. Let me find this one. It is a little more challenging. Because I know that's what you were wanting. We'll put one from homework on the thing. Well, maybe I didn't give you one that was like I'm thinking about. Okay, all right, we'll come back to that thought. So let's find an antiderivative this way. Okay. Using substitution. In words, okay. Really all we're doing with substitution is we're playing around with separating the du dx from taking the derivative, and you can call them differentials when you split them up. We haven't talked about that in here, okay, but that's what's going on. Okay. So one other application we're going to look at here. Okay. We'll come back to that one. Okay. That is definite intervals. Okay. Works the same way. Okay. We still need to get through the step where we get the antiderivative. Okay. There's just really only one other thing that gets added in. Okay. And let's just look at the rule. Okay. The only other thing that gets added in with definite intervals, and there's really two ways you can use substitution with definite intervals. Our textbook only talks about one of the ways, which is the better way, so I get why they don't bring up the not as good way. Okay, what you could do, okay, is you could ignore the limits of integration, find the antiderivative, get it back in terms of x, and then use the limits of integration that we started with. Okay. That's a little bit more work than the way we're going to do these. Okay. So the other way, okay, the slightly better way most of the time to do these is to, when we do our u substitution, okay, we're also going to change our limits of integration. And all we do, when we do our u substitution, we end up with an equation that says u equals something in terms of x. So all we do is we plug in the limits of integration for x and figure out what u would be. Okay? So like if we got some integral, okay, and we get this, we got like, so here's some integral, and we'll say it's like from 0 to 4. Okay? I have to put +1 there, sorry. Okay? So when we start, those limits of integration are in terms of x. But to figure out what they would be in terms of u, all we have to do is we just plug them in. So there, in terms of u, our upper limit of integration would be 9. And if we wanted to know the lower limit, you just plug in the lower limit. So plug in 0 for x. We would get 1. So then we could rewrite, sorry, it's going all the way around the slide. Then we could rewrite this as the interval from 1 to 9 in terms of u. Okay. So when we do this part, we get this equation, and we just use this equation with our limits of integration. We just plug both of these into this u equation, and that tells us what to write for our limits of integration in terms of u. Did I make that really confusing? No, not too bad. If I did, if you feel it's not bad at all, let's do an example. And that's not bad. So let's look at a definite one. Let's see. So we want the integral from 0 to 4 square root of 2x plus 1 dx. Okay. So we can do this with u substitution. Okay. You may want to make a trial on what to use for u. We could do 2x. The downside to just doing 2x is that then when we'll have square root of u plus 1, and then we're still stuck not being able to get the antiderivative. So we can add in a little bit more to our u, and it makes life a little easier. What else could we put in there? We can put in the plus 1. Yeah, then when we do the substitution, we'll just have square root of u, and that we can handle. Okay. So then du, take the derivative. So the derivative of 2x is 2. Derivative of 1 is 0, and then we'll write down our dx. Okay. So that part is u. The part that's left over is just dx. So we need to end up with something equals just dx. So again, same kind of idea as the ones we've seen. We can just divide both sides by 2 or multiply both sides by 1/2, and we get dx. So up to there, it's exactly the same as what we've already done. We're going to have square root of u. Well, I forgot the constant. We're going to have 1/2 the integral of square root of u du. Okay. The only part we're missing is we're missing our limits of integration. Up here, when we have the dx still there in terms of x, we need to figure out when x is 0 and x is 4, what would u be? So all we have to do to figure that part out is we use this equation, because it tells us u equals 2x plus 1. So when x equals 0, u will be 2 times 0 plus 1. So that's 1. And when x equals 4, our upper limit, u will be 2 times 4 plus 1. So we get 9. Okay. So back on our integral symbol, we'll rewrite our limits of integration. So 0 was the bottom one, it turns into 1. So our bottom one's 1. And then 4 was the top one, it turns into 9. No, that's 9. Okay. Makes sense. We're just plugging in for x to figure out what u will be. Okay. So then we need our antiderivative. The square root of u to the 1/2. So if we add 1 to the exponent, u to the 3/2, and then flip and multiply, so 2/3 plus c. And we want to evaluate this from 1 to 9. We don't have plus c, I'm sorry, because we're doing definite. I want to evaluate it from 1 to 9. So do the top number first, and we'll have a 1/2 times all of this. do the top number first. That's 2/3 times u, 9, to the 3/2 minus 2/3 to the, or times 1 to the 3/2. So good time for a calculator. It's not too bad though. Let's see. Square root of 9 is 3. 3 to the 3rd is 27. 27 times 2 is 54. And then that one's just 1. So we got 1/2 times 52/3. So we get 52/6, which is 26/3. And it's fine if you just punch that in the calculator from here and you have this equal 26/3. I'm fine with that. What do you think about that one? Bad? Think so? Let's see. Yeah. Yeah, you don't have to. Yeah, so that's the nice thing about this. By us changing the limits of integration in terms of u, we don't have to like do the extra step where we undo the substitution. Because we already got everything in terms of u, so then we just plug in for u. Yeah. So the alternate method would be to do this without changing the limits of integration, then undo the substitution, and then plug in for x, plug in 0 and 4 for x, and you would get the same number, but it's messier though, because instead of just plugging in 9 and 1, we'd have to plug in, we'd have 2x plus 1 there, so we'd have to do 2 times 9 plus 1, and it just makes it messier. So it's cleaner and shorter if you change the limits of integration to use. Yep. Yeah. So once you get here, it's just like what we did with the definite intervals before, right? You just plug in the top number minus what you get when you plug in the bottom number, and then it's usually some kind of messy arithmetic, and we get some kind of ugly number, usually. You want to do another one of those? I mean, do we need to do another one of those? Have to. Okay. I know you probably don't want to, especially on Friday. Because I mean, I could live without doing another one then. It was just, for my personal enjoyment, I wouldn't be doing it. So, kind of a silly question. Now, some people I work with, some people down the hall would be upset, like if they didn't get to do another integral today. I'm just not that into it, I guess. A lot of my coworkers stand around and talk about math all the time. I guess I would rather talk about something other than math. You'll have people in your profession, whatever you end up doing, that are the same way. You'll have some that are like so into it that's all they ever want to talk about, and some people that never want to talk about it. Okay. So let's just focus on the substitution part, and we'll worry about that it's a definite after that. So anybody see a U that might work? I think 2 plus 2x cubed is probably a pretty good choice. Okay. Then that whole thing will just turn into u cubed. It'll be easier to deal with. So then if we take the derivative of 2 is 0, that goes away. So then 3 times 2 gives us 6x squared, and then we'll put our dx. So we're almost there. The part left over is x squared dx, but we've got 6x squared dx, so yeah, I multiply both sides by 1/6 or divide by 6, however you want to think about it. X squared dx. Okay, so now that matches. So if we put our 1/6 out front, and our integral symbol, this thing turns into u to the third du. Okay. Then we want to rewrite our limits of integration, our little numbers on the squiggle, in terms of u. So we just take our u equation and plug in those values. Okay. So let's see, the top one, when x equals 1, u, what will we get there? We'll get 2 plus 2 times 1, we'll get 4. And when x equals 0, it's even easier. What will u be? Just 2. Yeah, 2. So now our limits of integration are 4 and 2. Every once in a while, u will be something weird, where when you change your limits of integration, the smaller number will be on the top and the bigger number will be on the bottom. That's okay, because remember, all that does, if we switch the top and the bottom number, is it puts a negative sign out front, and that works itself out. So you don't have to worry about it. If you have a smaller number on the bottom and a bigger number on the top, it'll be fine. So now we can find our antiderivative. So we're using the reverse power rule here. That would be u to the 4th, and then divide by 4, so 1/4. And if you wanted to, I didn't do it on the last one, but if you wanted to, you could pull the 1/4 out front as well. So that would be 1/24. It makes it slightly less you have to punch into the calculator. Anytime you have a constant, you can pull it out front if you want to. Okay. So then we'll have 4 to the 4th minus 2 to the 4th. 4 to the 4th, is that 216? 256. And then minus 16. So that's 1/24 times 240. This one comes out nice. Yeah. Okay. Need to back up. Doesn't all fit on screen, so. Okay. All right. So let me look over these real quick. So a few of them, to get you warmed up in the homework, tell you what to use for you, and then the ones that don't tell you what to use for you, you just have to pick it, and if it doesn't work, have to try something else. You get better at it the more of them you do. Okay. Let's do one more. We'll do an indefinite so we don't have to deal with that part. So while you're thinking about that one for a second, Monday, let's just work on any of these intervals that we need to work on. Okay? And then Wednesday we'll go through the practice test. Okay? I should be able to get the practice test posted by the end of the day today, so it'll be there if you want to go ahead and look at parts of it. Okay. So the reason why I'm giving you a heads up on that, I know it's holiday weekend, but try to at least look over these. Okay, that way if you've got major hang-ups on some of them, we can a week from today. Yeah. Okay, so anybody got any thoughts on you? I think x squared plus 2 is a good choice. And then when we take the derivative, we get 2x dx. So this part we've got covered. That's just going to be u. The stuff we've got left over is x dx. Yeah, so yeah, multiply by 1/2, divide by 2. Okay. So then this thing, two ways we could write it. We could write it du. Okay, so we could write it like this, and this is how a lot of the textbooks would write it. I've never liked that when they like incorporate the du into the function. The way I would rather see it is with the du out to the side. They mean the same thing, but I like having the du over there like the bookend on the end of the thing. Okay. Oh, and I forgot the 1/2. Yep. Good catch. So 1 over u squared, we can rewrite u to the -2. So then for our antiderivative, we add 1 to the exponent. Be careful there with the sign. And then divide by the new exponent. So divide by -1 makes it negative. Okay. And then we undo our substitution. So this will be -1/2 times x squared plus 2 to the -1 plus 2. Because it was negative u, so the negative can go out front. Or if you really wanted to, you could write -1 over 2 times x squared plus 2, and then plus c, if you want to get rid of the negative exponent, but you don't have to. Okay. Questions? All right. Proud of you that we're here today. All right. Well, see you on Monday. bring plenty of questions, and we'll work on those, and it'll kind of serve as an extra review day, and then we'll work through the practice test on Wednesday, and then have the test on Friday. Okay.